Today's topic is thermodynamic processes, which are basically some processes which an ideal gas undergoes in which heat is converted to work or internal energy is converted to work or the reverse. Okay. So there are four basic thermodynamic processes and infinite number of imaginary processes. Okay. First of such processes is called an isothermal process. Okay. As the name suggests, isothermal stands for a process or means a process which is carried out at constant temperature. Okay. Or you should not allow the temperature to vary significantly. Even if it's not perfectly constant, it should not undergo significant variations. Okay. So as the gas is being supplied heat and as the gas is expanding or being compressed, supplied heat or heat is being taken away from the gas also doesn't matter. As the process is carried out, as something is done with the ideal gas, its temperature must not be allowed to change. Okay, that kind of a process is called an isothermal process. Now see, being an ideal gas, okay, as I said, as far as your syllabus is concerned, the only system you are going to be uh, we are going to be learning about is an ideal gas. Being an ideal gas, the gas will have to obey this equation PV is equal to nRT. Okay, where n is the number of fine, let's discuss all the terms. P is the pressure of the gas, V is the volume, n is the number of moles, R is universal gas constant, and T is absolute temperature. Now, as I said, we won't assume the number of moles of the gas to be changing. We'll take a fixed amount of gas and make it undergo a process. So n remains constant. R is anyway constant. It's a universal constant. Okay, approximately 8.314 joule per mole per Kelvin. Okay. Now, in an isothermal process, temperature is also kept constant. If you keep temperature constant, that means the entire right hand side becomes constant. Therefore, you can say the product of pressure and volume will be constant in an isothermal process. Okay, temperature is constant. Therefore, the product of pressure and volume becomes constant. Pressure can vary, volume can vary, but their product should remain constant. Okay, that's what happens in an isothermal process. Now, if the product of pressure and volume is constant, you can say that pressure is inversely proportional to volume. Okay, therefore, at constant temperature, pressure of an ideal gas is inversely proportional to its volume. Okay, this is what is called Boyle's law. When I think Boyle's law, Charles's law, Gay-Lussac's law, these are more commonly used in chemistry. You study gaseous state in chemistry. Okay. There, these terms are more important. These names are more important. But anyway, so you can say that pressure is inversely proportional to volume and temperature is constant. Okay. Next, if pressure, if temperature is constant, P inversely proportional to V, then if a gas undergoes that kind of a process, how to indicate that process on a graph? Okay, that also you must know. Not just isothermal process, any process, any thermodynamic process an ideal gas undergoes, you should know how to indicate it on a graph. Okay, these graphs are called indicator diagrams or simply process diagrams. Okay, suppose you want to show how pressure varies with volume during an isothermal process. Okay, the PV graph, pressure volume graph of a thermodynamic process is a very common graph that will be given to you. As the process is carried out, how pressure and volume vary with respect to each other. Okay. So suppose you want to draw the PV graph. It is your choice whether you want to take pressure on the y-axis or volume on the y-axis. Generally, pressure is taken on y-axis and volume is taken on x-axis. It's not a rule, but usually it is done like this. Okay. And as we discussed yesterday also, pressure and volume of an ideal gas can never be negative. Okay. It simply doesn't make sense. Therefore, the PV graph, not just PV, any of the indicator diagrams, even temperature cannot be negative. So any of the graphs, pressure volume graph or pressure temperature graph or volume temperature graph will be in the first quadrant itself because none of these quantities can be negative. Okay. Temperature also cannot be negative if you take it on the Kelvin scale. On some other scale of temperature, it can be negative, but on Kelvin scale, it cannot. Okay. So suppose you want to draw the PV graph. You took pressure on y-axis, volume on x-axis. Now, generally, if you want to draw a graph, any graph, you need to know the equation or the relation between x and y. Now, the equation which relates pressure, volume, and temperature is the ideal gas equation, PV is equal to nRT. Now we are discussing an isothermal process. In an isothermal process, the product PV is constant. Now we took pressure on y-axis, volume on x-axis. That means, okay, pressure on y-axis, volume on x-axis. So y-axis is constant, or you can write xy is equal to constant. This will be the governing equation for this graph. Okay. And if you look up the graph for xy is equal to constant, the constant being positive. Okay. nRT is positive, no? So xy is equal to positive constant. If you see the graph will be a rectangular hyperbola like this. They are inversely proportional to each other. So when one increases, the other has to decrease. So if volume increases, pressure decreases. And if pressure increases, volume decreases. Okay, so this is how the graph looks. And the shape mathematically, it is called a rectangular hyperbola. That's the shape of the PV graph of an isothermal process. Okay. So let's just summarize whatever we discussed till now. One of the processes that an ideal gas can undergo, one of the thermodynamic processes that an ideal gas can undergo is an isothermal process. Means we maintain the temperature of the gas constant as we supply heat or remove heat from it. Okay. And then whatever happens to the gas happens. We'll discuss what all are possible also. Now, how an isothermal process is carried out also we have to discuss. But if you keep its temperature constant, then because being an ideal gas, it follows PV is equal to nRT, the entire right hand side becomes constant. So PV becomes constant. You can say pressure is inversely proportional to volume when temperature is constant. Okay. And if you draw the PV, pressure volume graph for such a process, this is how it looks. Okay. In many questions, just based on the graph, you will be expected to identify what kind of process it is. So it's very important to know how the indicator diagrams of standard processes look. Okay. Right. Now, the governing equation for this graph is PV is equal to constant. What was the constant? nRT, right? So if you keep temperature constant, the entire right hand side will be constant. You will get a graph like this. Now, with the same gas, at a higher constant temperature, you can carry out the process once again. Like, suppose once the graph was drawn at 300 Kelvin. Okay. So, you kept the temperature constant at 300 Kelvin and plotted how the pressure varied with volume. You got one graph. Okay. Next time, when you carry an isothermal process, let's say you maintained a higher temperature, a constant temperature of 400 Kelvin, and you carried out the process. Then you will see that if the same gas undergoes an isothermal process at a higher temperature, then the graph shifts away from the origin. It goes like this. So the first graph is at temperature T1, second graph is at temperature T2, T2 being greater than T1. So as you carry an isothermal process for the same gas at higher and higher temperatures, the PV graph will shift away from the origin. Okay. So such questions are also quite common. They'll give you two graphs and ask which one is at higher temperature. Okay. Right. So that is about the PV graph of an isothermal process. Next. The pressure, volume, temperature. These three are called the state variables of a gas because they indicate the state of the gas. So PV graph is one of the possible graphs. You can also draw pressure, temperature graph. Okay, any two of these state variables can be taken and drawn a graph. Okay. And you can draw a graph. Now, if you draw the pressure temperature graph for an isothermal process, we are still dealing with isothermal process only. Isothermal means what? Temperature is constant. Okay. Suppose you choose to keep pressure on the y-axis and temperature on the x-axis. Temperature is constant. Temperature is on x-axis. Means for this graph, the x coordinate will be constant. If the x coordinate is constant for a graph, then the graph goes like this. Pressure can vary, means the y coordinate can vary, but temperature does not vary. That's all. This is how the graph looks. It will be a straight line parallel to the pressure axis. So let's say this is a temperature T1. If you carry out the isothermal process at another temperature T2 and plot the pressure as a function of temperature, then it will look like this. Okay, temperature being constant, pressure can go up or down depending on the process. That's how the pressure temperature graph looks. Very easy. Temperature is constant, no? So only the other what other state variable will be varying. Next, volume temperature graph of an isothermal process itself. We are still dealing with isothermal process. In volume temperature also, temperature is constant, so volume will be the only thing changing. So it depends whether you want to take the temperature on x-axis or y-axis is your choice, or it will be given in the question. But suppose you take temperature on x-axis, again, x coordinate will be constant because it is isothermal process. Therefore, the graph looks like this. Volume may increase or decrease, but temperature should remain constant. So depending on the temperature at which the gas process is carried out, you will get the graph. Okay. So these are the uh, graphs for an isothermal process. PV graph, which is a rectangular hyperbola. Pressure temperature graph, straight line parallel to pressure axis. Volume temperature graph, straight line parallel to volume axis because temperature is constant. Okay. So for all the standard thermodynamic processes, you should know how the graphs will look. So we have done that part for isothermal process. Next. In an isothermal process, and not just in an isothermal process, in any thermodynamic process, you should know how to calculate delta Q, delta U, and delta W based on the information that is given to you. Okay, because in thermodynamics, that is our aim, how much heat is converted to work. Okay, so you should know how to calculate these three terms. Fine. Let's see. First, change in internal energy in an isothermal process. Can one of you quickly unmute and tell me the formula that we had discussed for internal energy based on Maxwell's law of equipartition of energy? Even today, we revised, okay, at the beginning of the class. Can one of you tell me the formula for internal energy? Quick. Okay. See, as I said, these are the only equations we'll be using in entire thermodynamics. Delta Q is NC delta T. Fine. N is number of moles, C is molar specific heat, delta T is the temperature change. Delta U is F by 2 NR delta T, provided number of moles and degrees of freedom does not change. Okay. Actually, U, internal energy, is F by 2 nRT, where F is degrees of freedom, N is number of moles, T is absolute temperature. And delta U will be F by 2 NR delta T. Okay, that's the basic formula for change in internal energy. Then delta W is integral PdV. That is how we calculate work done. Okay. And the other two equations, obviously, first law of thermodynamics and PV is equal to nRT. Ideal gas will have to obey PV is equal to nRT. Fine. So delta U generally is F by 2 nR delta T. So if temperature changes, then internal energy changes. Now, what kind of process are we talking about? Isothermal process. In an isothermal process, temperature doesn't change at all. Delta T is 0. That would make delta U 0. So in an isothermal process, the change in internal energy of the gas will be 0. Right. Next, work done by the gas in an isothermal process. Now, what is the general formula for work done by a gas? Delta W is integral P dV from initial volume to final volume. Okay. Now, in an isothermal process, pressure and volume can vary. Temperature should remain constant. Okay. So, gas may expand, gas may get compressed. Therefore, work will be done. Now, to integrate this, we need pressure as a function of volume. And usually, pressure, volume, temperature are related by the equation PV is equal to nRT. So, pressure as function of volume, if you want, you can get it from this itself. P is equal to nRT divided by V. That's all. That is pressure as a function of volume. You can always take help of the ideal gas equation. So here, work done in an isothermal process therefore becomes integral. In place of pressure, you can write nRT divided by V dV. From initial volume to final volume, we'll substitute the limits later. Now, this is like one of the problems that we solved, I think, yesterday itself. I gave you pressure as some constant divided by volume and asked you to calculate work done. We did integral P dV. In place of pressure, we wrote K by V, and dV. K was constant, we kept it outside. Then it became K integral 1 by V dV. And integral 1 by V dV is ln of V, natural log of V. You can do the same thing here. We are dealing with an isothermal process, right? In an isothermal process, nRT is constant. Then you can keep it outside the integral. So what will you be left with? nRT integral 1 by V dV. And integral 1 by V dV is natural logarithm of V. And we have to substitute limits initial volume to final volume. I'm calling it as V1 and V2. Therefore, the work done by the gas in isothermal process can be expressed as nRT multiplied with ln, substitute upper limit V2, minus ln, substitute lower limit V1. And ln A minus ln B is ln A by B. Therefore, work done in an isothermal process becomes nRT ln V2 divided by V1. Okay. So if you know the temperature at which the process is carried out, temperature is constant anyway in an isothermal process. So you should know the temperature at which it is carried out, and then from which volume to which volume the gas has expanded or compressed. You need to know the ratio of volumes, ratio of final to initial volume, then you can tell the work done. And in an isothermal process, PV is equal to constant, right? So initial pressure multiplied with initial volume will be equal to final pressure multiplied with final volume. So you can write V2 minus V1 as P1 divided by P2 also. Ratio of volumes can be expressed in terms of ratio of pressures. So the work done can also be expressed as nRT ln P1 divided by P2. So which formula you use depends on what information is given in the problem. If they give you the ratio of final to initial volumes, you will use V2 by V1. If they give you ratio of pressures, you will use P1 by P2. Okay. Now, I want you all to be clear here. In chemistry, okay, you have thermodynamics in chemistry also. There also you have a formula for work done in an isothermal process. So the chemistry formula for work done in an isothermal process, as far as NCRT is concerned, this is the formula that you have. I don't know about other uh, board syllabus. Can any of you tell me the formula if you have gone through thermodynamics in chemistry? I think you would have. In chemistry, they teach thermodynamics much earlier than in physics. Do you remember any formula for work done in an isothermal process? One of you unmuted but didn't say anything. Just tell if you remember, otherwise leave it. Okay. In chemistry, the formula you have for work done in an isothermal process is, I think, minus 2.303 nRT logarithm of V2 divided by V1. Okay. First, where did the minus come from? In chemistry, the delta W that you learn about is work done on the gas. Okay. In fact, the first law of thermodynamics itself is written differently in chemistry. We are using delta Q is delta U plus delta W. In chemistry, they write it as delta Q plus delta W is equal to delta U. That means they write it as delta Q is equal to delta U minus delta W. In physics, we have a plus here. In chemistry, they have a minus here. Why? Because in chemistry, delta W stands for work done on the gas. Means how much energy we are supplying to the gas in the form of work. In physics, we don't do that. Why? Because in physics, in the thermodynamics that we study in physics, we are interested in converting the gas, converting heat to work. So the gas should do the work. We won't be doing work on it. Fine. But in chemistry, energy will be supplied to the gas in the form of heat and also in the form of work. So in chemistry, the delta W you have is work done on the gas. In physics, the delta W you have is work done by the gas. That's why, and they are automatically they are negatives of each other. If work done on a system is 200 joules, then work done by the system will be minus 200 joules. Okay, they are negatives of each other. That's why you have the minus sign. Okay, so that explains the minus in the work done in chemistry formula. So let me write it here. Work done on the gas. That's why you have a minus. And where did the 2.303 come from? In physics formula, we don't see that. Okay, because here, see, integral 1 by v dv is natural logarithm, ln of v2 by v1. When you, natural logarithm means like when you write ln x, that is nothing but logarithm of x to the base e. E is a special number in mathematics. Okay. But when you write log of x, it's like logarithm of x to the base 10. These are different functions. And ln of x, which is logarithm of x to the base e, can be written as 2.303 times logarithm of x to the base 10. Fine. So in the physics formula, you have ln v2 by v1. In chemistry formula, you write log v2 by v1. So when you change ln to log, you'll get this 2.303 factor. Okay, that's why in chemistry, you have that formula for work done on the gas in an isothermal process. Okay, fine. You don't have to remember any natural logarithm values. They will give you in the question paper if required. So what have we discussed so far? That change in internal energy in an isothermal process will be zero. Why? Because internal energy depends on temperature. Because we are not going to change the degrees of freedom or the number of moles. It only depends on temperature. And in an isothermal process, temperature is not changing. So internal energy won't change. That is zero. And work done in an isothermal process can be calculated as nRT ln V final by V initial. And remember, this is being derived from PV is equal to nRT, right? PV is equal to nRT is valid only if temperature is in kelvins. So here also, it is compulsory that temperature is in Kelvin. You cannot substitute temperature in other units and calculate work done using this formula. Okay, right. So we got expressions for delta U, we got expression for delta W. And if you know delta U and delta W, from the first law of thermodynamics, the way we write it in physics is like this: delta U plus delta W, where delta W stands for work done by the gas. We know that this is 0, and we know that this is nRT ln V final by V initial. Then that itself will be the heat supplied as well. So basically what happens in an isothermal process is, okay, or you can write third case, delta Q in an isothermal process. Okay, since delta Q is delta U plus delta W and delta U tends to 0, delta Q itself will be delta W. Therefore, in an isothermal process, all the heat supplied, delta Q stands for heat supplied, no? All the heat that you supply to the gas converts to work. work done by the gas. Okay, that is what essentially happens in an isothermal process. Fine. So if delta Q is positive, means you are actually supplying heat, delta W will be positive, gas expands. If delta Q is negative, that means if you are removing heat, delta W will also be negative, means it will get compressed, its volume will decrease. That is what happens in an isothermal process. So we have drawn the process diagrams, like we have discussed how the process diagrams look, and we have discussed how to calculate delta U, delta W, and delta Q in an isothermal process. These are the basic things that you should be able to do for any kind of process. Okay. Next, molar specific heat of an isothermal process. Now, molar specific heat is seen in this formula, delta Q is equal to NC delta T. So you can say molar specific heat is delta Q divided by N delta T. Now in an isothermal process, the change in temperature is zero, or as I said, it must be negligible. The temperature should not change significantly. We will supply heat, but temperature should not change. How that is possible also we'll discuss. Okay. So heat will be supplied. So numerator is non-zero, but temperature change will be tending to zero. Numerator is a significant non-zero value. Denominator tends to zero. Then what will happen to this fraction? Tell me quickly. Numerator non-zero, but denominator zero or tending to zero. What will C be tending to? Non-zero number divided by something tending to zero, the value will tend to infinity. Therefore, molar specific heat of an isothermal process tends to infinity. Next, remember how we derived this. Delta Q is equal to NC delta T. That's the basic formula involving molar specific heat C. So C becomes delta Q by N delta T. From there, we comment on what will be the molar specific heat for this particular process. You can do that for any process. Next, bulk modulus. Bulk modulus of a gas when it undergoes this kind of a process. Now, by definition, if you all remember, bulk modulus is nothing but volumetric stress divided by volumetric strain. We had discussed this in the chapter mechanical properties of solids. Okay. We applied this in fluids also. Volumetric stress is nothing but change in pressure divided by volumetric strain is nothing but delta V by V. And this comes with a negative sign because if pressure increases, usually volume decreases. If one is positive, the other will be negative. And to make the whole thing positive, we put a minus sign. Now, when it comes to thermodynamics, we write bulk modulus like this. Okay, like this same expression can be written as minus V delta P by delta V. In thermodynamics, we use this as minus V dP by dV. Okay, that is how we generally express bulk modulus in any thermodynamic process. We don't use delta, we use d, small changes. Okay, now we need to apply this to an isothermal process. In an isothermal process, okay, process specific bulk modulus we want to derive. In an isothermal process, the product PV is constant, pressure is variable, volume is also a variable, but their product is constant. Okay. Since we need dP by dV, this can be obtained by differentiating the process equation. Process equation is this. You can differentiate ideal gas law also, PV is equal to nRT. From there, you can get dP and dV, or the ratio dP by dV. Fine. Remember, these are some of the approaches. Because in questions, you may be asked, what is the bulk modulus for so-and-so process? So understand where to get it from. Okay, bulk modulus by definition is minus V dP by dV. Since you need dP by dV, like you need to know rate of change of pressure with respect to volume. One thing you can do is differentiate the ideal gas equation. Another thing you can do is differentiate the equation particular to that process. Okay. Now pressure is variable, volume is also variable. So there are two variables. And you need to differentiate this. So you'll have to apply the product rule. How to differentiate the product of two variables? Keep the first one constant, differentiate the second one. You can differentiate with respect to any variable you like. Plus, keep the second one constant and differentiate the first one. And right hand side is a constant. Constant derivative is anyway 0. So this dx is going to get cross multiplied to the other side and it becomes 0. Therefore, p dv plus v dp becomes 0. Understand the approach. Okay. We wanted dp by dv. So where do we find pressure and volume in a single equation? Ideal gas equation or the process equation. The process equation for an isothermal process is PV is equal to constant. We are differentiating it. Okay. So you can write P dV is minus V dP. And what did we want? Bulk modulus is minus V dP by dV. Now send dV to that side. So minus V dP by dV is nothing but pressure of the gas. So the pressure of the gas itself is the bulk modulus in an isothermal process. Okay. And definitely pressure is a variable. During an isothermal process, pressure varies. That means bulk modulus of the gas varies. What does bulk modulus basically mean? See, Young's modulus, shear modulus, bulk modulus. These are the three moduli of elasticity that we had learnt about. They indicate how elastic a system is or an object is. How elastic means what? How hard it is to deform that system. Higher the modulus of elasticity, harder it is to compress or elongate that object. Okay, to compress or enlarge that object. So same thing with bulk modulus. Higher the bulk modulus or greater the bulk modulus, more difficult it will be to compress that object volumetrically, to decrease the volume or to increase the volume also. Okay, so we see that in an isothermal process, bulk modulus is the pressure of the gas itself. So what this means is greater the pressure of the gas, greater the difficulty to compress the gas. Okay, in an isothermal process. Okay. So we have discussed how to calculate molar specific heat. For isothermal process, it will be tending to infinity. And we have discussed how to express the bulk modulus as well. Right. So drawing graphs, then knowing how to calculate delta Q, delta U, delta W, and then knowing how to calculate molar specific heat and bulk modulus. These are the fundamental things you need to know in this chapter thermodynamics, and we'll be doing this for all the standard processes. We have done it for an isothermal process now. Okay. Little bit of mathematics will be involved. You have to get used to that. Okay. Next question. How to carry out an isothermal process? Isothermal means what? Temperature should be constant. We will supply heat, but the temperature should be constant. Can any of you tell me how this is possible? Think about it for a minute. How to carry out an isothermal process? Okay. We want the temperature of the gas to remain constant even when we supply heat. Now, when you supply heat, basically what happens to the system? One thing that can happen is temperature rise, means internal energy increasing. The other thing that happens is work done. Now, we don't want the temperature to rise. So what you can do is supply heat slowly, very slowly, and allow sufficient time for the gas to expand. Or the reverse, if you are actually removing heat, allow sufficient time for the gas to contract or get compressed. If you do that, then its temperature won't change significantly. Okay, so you'll supply a little bit of heat, wait for the gas to expand, wait for temperature to come back to the starting temperature. Temperature may increase slightly, but if you allow it to expand, no, temperature will come back to initial temperature again. Next, you again supply a little bit of heat. Temperature rises a little bit, but if you again give time for it to expand, temperature will come down to the initial value. So that way you keep supplying heat slowly, the gas will keep expanding without significant change in temperature. That is how an isothermal process is carried out. Okay. So it goes without saying that isothermal processes are definitely slow processes. You cannot expect isothermal process to take place quickly. Sudden compressions, sudden expansions cannot happen in isothermal process. Only a very slow expansion of gas or very slow compression of gas can be done isothermally. Okay, so if you want to actually carry out an isothermal process, this is how it is done. And this point is important also. You'll understand why. Okay, in further chapters, you'll understand why. So isothermal processes are not quick processes. Okay, keep that point in mind. Fine. Let's solve a few basic problems on isothermal process. First, let's say, okay, 5 moles of diatomic gas are expanded isothermally. Okay, EXP is for expanded. Expanded isothermally at what temperature? Let's say 27 degrees C from an initial volume, let's say V naught, to a final volume of 3 V naught. Okay. Let me give you the volume also. Let's say initial volume is some 10 meter cube. See, it's quite common to express gas volume in liters. Okay. And you should know how to convert liter to meter cube. 1 meter cube is 10 power minus 3, sorry, 10 power 3 liters. 1000 liters can fit in 1 meter cube. Okay. You need to keep this conversion in mind. Okay. So 5 moles of a diatomic gas are expanded isothermally at 27 degrees, means maintaining constant temperature of 27 degrees. We expand it from initial volume 10 meter cube to 3 times of that volume. Okay. So you know everything. Number of moles of the gas is given, type of gas is given, and what exactly is being done with it is also given. Then calculate all these. First, how much is the work done by the gas? Okay. In physics, delta W stands for work done by the gas itself. Okay. So you need not be told that whether it is by gas or on the gas. You have to find out work done by the gas unless asked otherwise. Okay. Find out work done by the gas and next find out the heat supplied to the gas. Okay. Calculate these two. I'll give you all 3 minutes. Okay. I haven't received any answers yet. Can one of you quickly tell me the formula for work done by a gas in an isothermal process? Work done is calculated as nRT ln V final by V initial. Okay. Maybe I should specifically give you some time to note down the formula while explaining. Okay. Just substitute all these terms. The number of moles is given to you in the problem as 5. R is 8.314. In SI units, it is 8.314 joule per mole per Kelvin. Okay. Temperature at which the process is carried out is 27 degrees C, that is 300 Kelvin. ln V final by V initial. Final volume is 3 times the initial volume. So that becomes ln3. And you can keep it as it is. You don't have to know the value of ln3 or substitute the value of ln3. That's all. This is the answer. You can do that multiplication also. Okay. And because we have substituted everything in SI units, you get the work done in joules. So this much work will be done by the gas. And the answer is positive because the gas is expanding. Okay. If a gas expands, work done will automatically be positive. Work done by the gas will be positive. Okay. Second part of the question was how much heat was supplied to the gas. Now, for heat, you have this equation Nc delta T. But you won't be able to use this equation because in an isothermal process, C will be tending to infinity. Okay, you don't know its exact value. So you won't be able to use that equation. In most thermodynamic processes, that will be the situation. So you will have to use first law of thermodynamics. Delta Q is delta U plus delta W. In isothermal process, delta U is zero. Temperature doesn't change, so internal energy doesn't change. Therefore, heat supplied to the gas will be the work done by the gas itself. So the same answer for delta W you'll write here. That is the heat that must have been supplied to the gas. Okay. So you didn't actually have to know what kind of gas it is. Monatomic, diatomic doesn't matter. Polyatomic. Okay. Exact volume also doesn't matter. You just need to know the ratio of volumes, final volume to initial volume to answer this problem. Fine. So let's summarize isothermal process. Basically, it's a process which is carried out at constant temperature. Because the temperature is constant and being an ideal gas, it has to obey PV is equal to nRT. It becomes PV is equal to constant because number of moles is not going to change. If you introduce extra gas, means if you increase the number of moles, or if you remove existing gas, that means if you decrease the number of moles, then PV won't be constant. N can change. But usually, as far as physics problems, thermodynamics and physics is concerned, N will not change. Then you can write PV is constant, pressure is inversely proportional to volume. We drew process graphs based on that. Then we derived equations or formulas for delta U, delta Q, and delta W in an isothermal process. Remember how all these were done. We used the basic formula for each of these terms. Delta U basically is given by F by 2 NR delta T. Apply that to isothermal, it becomes 0. Delta W basically is given by integral P dV. Apply that to isothermal, it changes to nRT ln V final by V initial. Okay. And delta Q is delta U plus delta W. From there, you can tell the heat supplied. Based on that, you get molar specific heat, bulk modulus. Okay. And we discussed how the process can be carried out. Okay.